Good evening. Thank you for joining us tonight for the first session of our RiverWatch Fall Speaker Series. For those of you who are new to the Illinois RiverWatch Network, RiverWatch is a citizen science organization that trains volunteers to monitor water quality in their own communities. The mission of RiverWatch is to safeguard the future of Illinois rivers and streams through stewardship, education, and sound science. I'm going to start off with a couple of housekeeping items. First, I ask that you keep your microphone muted during the presentation to limit distractions from sirens, barking dogs, and noisy neighbors. If you have a question along the way, you can either put it in the chat box and Megan can answer it at the end, or you can save it and ask it aloud during the question and answer session. Now with that, we are very pleased tonight to welcome Megan Pagliaro. Megan graduated with her Bachelor of Science and Master of Science from St. Louis University. She is currently a PhD student in the Ruhi Lab in the Department of Environmental Science, Policy, and Management at the University of California, Berkeley. Tonight, Megan will talk with us about the work she has done looking at how urban heat islands are impacting fish in freshwater ecosystems. Thank you, Megan, for being here, and we look forward to hearing what you have to say.
Hopefully that everyone can see. First, I'd just like to say hello and good evening. I hope, well, thank you all for coming to my talk. I'm very excited to talk about this research. And while I'm currently a PhD student at UC-Berkeley, I will be talking about the work I did as a master's student at St. Louis University. So this is the, nope, there we go. The outline for my talk. I'll first cover the introduction as well as some background on the subject. Then I'll move on to study design, which will lead us into methodology. And I will finally talk about the results and conclusions near the end. So to get us started, right off the bat, my study is looking at the effect that environmental changes have on freshwater systems, such as lakes and streams, as well as the organisms that live in those systems as well. But there are two main types of environmental change that I will be focusing on. And those are global climate change and urbanization. So to start with global climate change, and what is meant by that, global average annual temperatures have increased by about 0.7 degrees Celsius from pre-industrial standards and show no signs of stopping. According to current research on climate data through the IPCC, which is the Intergovernmental Panel on Climate Change, they predict that we will hit 1.5 degrees Celsius of warming between the year 2030 and 2052. So it's less of a matter of if we will hit this temperature, but more when. So what does this mean? What is the effect of the warming that we've already seen, and what will be the effect of the warming we will continue to see? And as such, so global climate change is mainly characterized by increases in temperature and increases in environmental variability. With increased temperature, we will see higher temperature extremes. So hitting just higher and higher levels of extreme high temperatures, and even we'll see periods of extreme low temperatures as well. So uncharacteristic high and low temperatures, but is mainly characterized by hitting more temperature extremes in the warming section. And then with increased environmental variability, I like to explain that in terms of precipitation. So what it means is not necessarily that the amount of rainfall will change over a given time period, but when it rains, the frequency of rain, as well as the intensity of each event can becomes more sporadic. So as seen through this figure, I don't know if, hopefully you guys can see my cursor, but that black line is generally, let's say, the average precipitation fall in, I believe it's New Mexico. Yes, and as the years develop, as as you see, we're just reaching higher and higher amounts of precipitation some years, and then in other years, it's reaching like new lower. So it's the high variance along this kind of median precipitation line that will continue to get more sporadic and change. And so that's both seen through precipitation and drought. So that is what's essentially occurring around the globe. But if we want to zone in on a smaller scale, land use is also changing in terms of urbanization. So with urbanization, the UN predicts that 68% of the world's population will reside in cities by 2050. This is resulting both from population growth as well as a movement of that population from rural to urban areas. So cities will have to expand at a rapid rate in order to support this influx of 2.5 billion people. So what these two environmental changes show us is that there is, this is all happening on a rapid scale. So we're gonna see expanding urbanization as well as these changes in environmental variability as well as temperature increases in a very short period of time. So now that I've laid out this background on these environmental changes, I do want to highlight a key pattern from this information and how I presented it. And that is, it is all in the context of a terrestrial or land-based system. So meaning we're tracking air temperature as well as focused on the movement of individuals and people from land. And this is how the context of both global climate change and urbanization are often presented in research. It is through this context of it being a terrestrial or land-based system. But as an aquatic ecologist, I wanted to know what these environmental changes mean for freshwater systems and freshwater species. Because freshwater systems are a little more complicated for a few reasons. So here I outlined some of the main reasons which make freshwater systems particularly special. First is variations in sensitivity to air temperature. And so if we turn to this figure, in this gray dotted line is fluctuations in air temperature. And for aquatic systems, some of these systems will closely track that fluctuation, as seen with that red line, and how it tightly follows the changes in air temperature. Even with that though, water still has what's known as a buffering effect, in that it takes a lot more energy to heat or cool water than it does to heat or cool air. So there will still be always this gap and difference between air temperature and water temperature. But again, so some systems though will still track those changes fairly closely and be highly affected by changes in air temperature. There's also water systems though that have very little change in response to changes in air temperature, as seen with this blue line. So while there are slight shifts, overall their air temperature has very low influence on these systems, and they're called low sensitivity systems. So this is maybe seen as a spring-fed stream, so a stream which gets a high input of water from an underground spring source that is cooled constantly. So that means that there's constantly an input of cool water that that is basically stabilized regardless of the season. The other aspect of freshwater systems that are interesting is they have a less defined temperature gradient. So with land-based systems, there's commonly known a latitudinal gradient of temperature. So that means that temperature is cool as they get towards the poles and warm as they get towards the equator. With freshwater systems, this is a much less defined temperature gradient, and it's a weaker relationship. As with altitude or elevation is another major component, or possibly a stronger component, which determines water temperatures. So here's a map of the streams in the Northwest United States, and they're colored based on temperature, with blue being the coolest and red being the warmest. And as you can see, the cool temperatures are tracking these mountain ranges and high elevation systems. So it more has to do with a trend in the differences in elevation than it does with a latitude gradient. So meaning getting colder or warmer, depending if you move north or west. All right, so we know that these freshwater systems are complex, but what about the species that live within them? It turns out they also have a complex relationship with water temperature as well. So freshwater fish and many freshwater organisms are ectotherms, meaning their body temperature is regulated externally through their environment. That means that processes such as metabolism, growth, reproduction are all dependent upon and influenced by the temperature of their surroundings. As such, essentially all freshwater ectotherms have a range of temperatures known as a thermal tolerance, where these processes are optimized. And if the organism ever comes in contact with an environment outside of that temperature range, so outside of that thermal tolerance, it can be detrimental or even fatal to the fish. So on top of that close relationship with the temperature of their environment, freshwater organisms also have reduced migration ability compared to terrestrial organisms. And to bring back that map from a slide ago, this actually quite nicely represents how migration and distribution issues, so meaning like restrictions in movement for freshwater organisms. If they're located in, let's say, this lake, and there aren't really any stream accesses to that lake, then all organisms found in there are highly restricted and can't move outside that lake. So that is a high restriction. They also experience moderate movement restrictions, and this is seen in these stream systems. All organisms must keep to this system. So if the fish is located in this area here and needs to get to cooler temperatures, while there is some possibility of movement, overall, if the stream doesn't connect or there's a dam or other impediment, then there are no other options in order for the fish to move elsewhere. So unlike terrestrial organisms, which have the potential to theoretically move in all directions, freshwater organisms and freshwater fish are stuck to these networks. I'm going to pause real quick too, just say I don't have access to see the chat. So if there are any issues with audio or major questions, someone may have to pop in and stop me. So
we're doing good.
Woo! Also, a slow down, Megan, is okay as well. Alrighty. So, oops. So now that we see basically how complex these both freshwater systems as well as the species within them and their relationship with these temperature are, the need to understand and predict the impact of rapid increases in water temperature, as seen with global climate change and urbanization, is increasingly important. But this kind of knowledge gap leads me to the next portion of my presentation, and that is the study's design. And that is because essentially this question leads us to another question. How could we study this? So is there an experimental system in which we can study how freshwater organisms, such as freshwater fish, respond to this intense warming or change? And does such a system occur naturally, as in is it readily available? The answer is no. Thank you for coming to my talk. It has been a great day. Just kidding. Yes. So this is where urban heat island effect comes into play. The urban heat island effect is a phenomenon where air temperatures in urban areas are significantly warmer than nearby non-urban areas. And this is due to a few things. First, the high heat storage capacity of building materials. Second, the disruption of energy transfer processes such as airflow, so reduced cooling abilities. And additionally, an alteration of evapotranspiration rates, so the rate of evaporation and transpiration. And this is due to the high levels of impermeable surfaces in cities. So impermeable surfaces are areas like streets, sidewalks, roofs, all areas where rainfall cannot seep into the ground and instead either pools or runs off it. So due to all these effects, essentially there is an increased heating within these urban cores. Urban heat islands are readily available. They're found all over the place. They're historically documented, meaning they have most major urban cores have developed within the last 100 years. And yet they're still subject to environmental variations, which you can't replicate in a lab. So they're still essentially like any type of lake or stream located in an urban area is still subject to different environmental effects and processes that really can't be replicated in a lab. So this makes them ideal systems to understand rapid increases in temperature associated with climate change. And lucky for me, there was an urban heat island right in my backyard. So this is a plot of the air temperature in St. Louis compared to a nearby non-urban area, Quincy, Illinois. And this was just picked because it was the closest place that wasn't a city and, wasn't a massive city and had historical air temperature data. But essentially, each of these points is the difference in air temperature between St. Louis and Quincy, with all those above this line being warmer in St. Louis and all those below being warmer in Quincy. So over the past, since 1920, there's been a slow increase in temperature differences between St. Louis and Quincy, which is indicative of the development of an urban heat island in St. Louis. St. Louis City is almost 3 degrees warmer than this nearby non-urban area. Additionally, both lake and stream freshwater systems can be found within St. Louis and across an urban gradient. So I have a readily available experimental system which I can use to develop the goal of my research. And the goal of this research is separated into 2 main parts. I first wanted to determine whether streams and lakes in urban systems have warmer water temperatures compared to non-urban streams and lakes due to this urban heat island. And second, I wanted to see if fish populations in these urban lakes and streams have higher thermal tolerances, meaning they can withstand higher temperatures than those found in non-urban populations. So the study design focused on studying both streams and lakes, so those 2 components, and then I wanted to look at 1 fish species in the stream and then 1 fish species in the lake. So the fish I looked at in the stream, studied the central stone roller, scientific name Compostoma anomalum. This is a minnow that feeds primarily on benthic algae. So that is algae that grows on the bottom of the lake or stream. They are distributed within eastern and central North America and are highly abundant in stream and river systems in Missouri. For the lake component, I looked at bluegill, scientific name Lepomis macrochirus. They feed primarily on aquatic invertebrates and other invertebrates, meaning bugs. Their native range is central North America, but that range has expanded widely due to movement of the species for stocking and fishing practices. They are highly abundant in Missouri lakes and also commonly stocked in Missouri lakes. So with my fish species chosen, I developed my hypotheses. And this is essentially what I am trying to prove through this research project. My first hypothesis is that urban stream populations of central stone roller will have higher thermal tolerances compared to non-urban populations. So within that, it includes that urban streams will have higher warmer temperatures compared to non-urban streams. And then the second hypothesis is that urban lake populations of bluegill will have higher thermal tolerances. So again, they will be able to withstand warmer temperatures compared to non-urban populations. And within this hypothesis too, I am assuming that that urban lakes will have warmer water temperatures than non-urban lakes. All right, and now that I have covered the hypotheses, I can finally answer a question I know that has been on everyone's mind. And starting off, so now we're at the methods portion, but how will I study this thermal tolerance? And I chose method of critical thermal maximum, CT-max. So there are many methods of measuring thermal tolerance in fish, but this is the method we chose because it requires fewer fish, is cost effective, time efficient, and it better reflects natural conditions. And that is because it involves testing on a constant rate of temperature change. The only other thing I want you guys to take away from this is that this test requires, what it requires is a kind of defined endpoint, and this is an endpoint before physiological death, so actual death. It's a defined endpoint which is called ecological death. And this is when those physiological processes that I talked about, like metabolism and growth, etc., are no longer able to function properly. So they've hit a temperature outside of that thermal tolerance, and then one of those processes is disrupted. A common endpoint, and the endpoint I will use, is loss of equilibrium. So that's when a fish loses its ability to correctly right itself, so then it turns upside down and it goes belly up. And again, this is before actual death, but it is where in nature, if a fish is belly up, then it is prone to predation and can no longer reproduce, etc. So it's called ecological death. But that is that moment when the fish has hit its highest possible thermal tolerance before, and that's that point that we are measuring. And then a few things with this test have to be controlled for, such as like the temperature, making sure that all the fish acclimate to the same temperature, and then also standardizing body size, but we can move past this. But anyway, this test requires me to collect fish and bring them back to that lab to undergo acclimation and then to test. So I had to pick my sites and begin collecting fish. This figure is showing the location and surrounding land cover of my 11 stream sites where I collect the compostoma, the central stone roller, and 12 lake sites where I collect the bluegill. Each site is also the location of a temperature logger, which is collecting water temperature data. And just to quickly explain, the forested land cover is seen as the variations in green. The red is urbanized land cover, with pink being low urbanization, red being high urbanization. All of these sites located in St. Louis City are undergoing high levels of urbanization. So at each of these sites, like I said, I deployed water temperature loggers to collect data on maximum water temperature. So we were interested in looking at that maximum temperature that each of these systems are reaching. We collected that data from July 2018 to August 2018. And we focused only on the summer months because in temperate areas like St. Louis, essentially everything freezes in the winter. So we're going to see that highest difference due to the urban heat island during the summer months. So at each of those sites, I collected 25 to 30 individuals within a standardized size range and brought them back to lab. Once they're in the aquatics lab at St. Louis University, all individuals were acclimated for 2 weeks at the same temperature. Again, that standardization that the CT-max test needs. And this was done through dual chiller heater system to just help maintain that temperature and accuracy. And then after the 2 weeks, I did the CT max testing. And it was through this system. So to quickly kind of run through what this system involves, there's 2 hot water baths, and those are run the heating for this for the whole system, and they will heat the water at a constant rate, which is required for that CT max test. There's also a mixing reservoir with a mixing pump, and this is so that we eliminate any differences in warming between those two different machines. And then that water is pumped into these 2 test chambers. Within one of these test chambers, each cup represents 1 site. So we'd have 11 cups for the stream sites with the stone rollers, and 12 cups for the lake sites with the bluegill. And each cup holds a single individual. And then that is just simply mirrored in that other chamber. So this whole test system allows us to test 2 fish from each site at once. And then this is just another diagram of how the water moves through that system. So again, it's pumped from this tank into the hot water bath where it's heated, then from the hot water bath to the mixing reservoir, and then back to the testing tank. And now, once these tests were run, I have the data on the thermal tolerance. So now we're moving on to the results. So for both the results and conclusions, I'm going to be discussing them in 2 parts. The first is talking about the effect of urbanization on the water temperature of the lakes and streams, so with those sensors we're collecting. And then after I talk about that, then I'll move on to the information from the fish component of the study, so the thermal tolerance. So again, to start off with the water temperature, we saw there was a significant difference between water temperature with percent urbanization. So this figure is just plotting those maximum water temperature across percent urbanization. The non-urban sites had less than 15% urbanized land cover. And as you can see, there's quite a range of maximum temperatures from these sites. And this is actually reflective of that slide in the introduction with the difference in sensitivity of these systems. So with the gray, red, and blue lines. So these 2 sites are ones that have lower sensitivity to air temperature, so they're cooler despite the summer months. And so those will follow that blue line. And then these sites more closely track differences in air temperature, like the red. So it's just kind of a cool way to see that figure actually come into play. And then, so these are the urban sites. They all had greater than 95% urbanized land cover. And as you can see, not only are they warmer than the non-urban sites, but they're also more tightly clustered. So we've lost that variation in temperature differences and sensitivity differences. So now for the lake sites. So again, looking at maximum water temperatures, so water temperatures over that percent urbanization. And we actually found no difference between the urban and non-urban lakes. So there was no significant temperature difference. These are the non-urban sites. They have less than 35% urbanized land cover. And these are the urban sites. So, and they had greater than 80% urbanized land cover. But again, as you can kind of see overall, there's really no clear trend for water temperature here. But another interesting component is what's happening on this axis here. So this is actually a much more narrow range of temperatures than we saw with the stream sites. And so I'm just going to put that in context by, I'm going to show a figure next, and I'm literally just pasting the stream temperatures, their maximum temperatures, that figure you just saw before for the streams, on top of the lake ones. So they'll be plotted together. So as you can see here, this is all the lake sites. They have much more narrow of a temperature range. compared to that of the streams. So this is the non-urban streams, urban stream sites, and then the blue is these are the non-urban lakes, and then the urban lakes. But overall, even the non-urban lakes have, like, they're much warmer, as well as they're in a very narrow temperature range. And I'll explain some possible reasons for this, explanations, etc. in the conclusion. Now on to the thermal tolerance portion. So for the central stone rollers, these were the ones in the stream sites. We saw urban populations can withstand higher water temperatures. So the urban populations had a significantly higher critical thermal maximum, that CT max, than non-urban populations. And then for the bluegill, those are the ones in the lakes. We found that there was no significant difference in thermal tolerance between the urban and non-urban populations. So, meaning that there was no difference in the ability to withstand warmer temperatures between those that were in the urban sites and those that were in the non-urban sites. And again, I will discuss that in more detail later in the conclusion, which is starting now. So again, I'm going to first talk about conclusions with the differences in water temperature, and then I'll move on to the conclusions with the differences in thermal tolerance. So with the stream sites, to wrap up, we saw that urban sites are significantly warmer, and we saw that urban sites lost variation in temperature. So they lost that range of sensitivity. Another interesting component of streams. So as seen from this picture, streams and rivers have a constant mixing and churning of water. That means that there's less of an ability for water to separate in temperature, and warming has to include the whole body of water at one time, which we like, so essentially equal warming of that stream. So that means that species found within the stream are going to be subject to the heating and can't essentially move away from that unless they move out of like the stream itself to another stream network that is cooler and not under those heating mechanisms. So that would make sense that why urban streams are clearly warmer is because it is a full heating of the system compared to non-urban streams, which aren't under that urbanization pressure. For the lake sites, we saw no difference in water temperature with urbanization. And so we think this may be due to a few things. First, the location of the temperature loggers. So we all put the temperature loggers for the lakes in the same depth. And it's possible that at the depth we put it at, essentially it was so shallow that all the water just heated to the same amount. So that could be explained, that very narrow temperature range. So the loggers were not able to capture the differences in temperature, which happen maybe at deeper depths, higher depths. But and again, I'll explain why that would be in a second. But then another possible reason is a few of the urban lakes had the city pumps chlorinated cooled water into the lake in order to keep the temperature a bit lower to stop from fish kills happening in the summer. And this is only in a few of the urban lakes we looked at, so not all of them, but it could be a possible explanation for why there was no difference in temperature. And so, and then to explain another phenomenon with lakes is that they undergo something called temperature stratification in summer. So this is a separation of temperature into zones where there's a warmer temperature zone, and then as you move deeper, it gets cooler and cooler. So this means that species that live within a lake have the ability to move to cooler temperatures if where they're located gets too warm, so just moving deeper. But what that can also mean is that, again, if my logger was too shallow and that heated too quickly, the temperature changes may be happening lower in the lake. So, but what is this overall, what do we want to take away from this water temperature component? And one is that these two freshwater systems are responding very differently to air temperature. So it's not even as simple as looking at freshwater systems as a whole versus terrestrial systems when looking at the influence of global climate change or urbanization. It is freshwater systems themselves are very different, but then from terrestrial. But then even within that, from lakes and streams, they are responding very differently and need to be looked at as separate units. And so like that kind of comes to the second point, that the urban heat island will not impact freshwater systems the same way it impacts terrestrial systems. And as such, freshwater systems need to be studied as well. So from that, now we're going to move on to that thermal tolerance conclusions. So for the central stone rollers, those were the stream fish, we saw an increased thermal tolerance in response to a rapid increase in temperature. So it shows that the fish does have an ability to adapt to rapid increases in temperature. One thing though is our study does not look at how. So, or it doesn't look at, essentially the mechanism. We know that the fish can respond, but we don't know what about them gives it that ability to respond. So that is where this research can be expanded upon and continue to look at. For the bluegill, we saw no difference in thermal tolerance between the non-urban and urban populations, and there'd be maybe a few reasons for this. The first is, like, let's say that if we were not able to properly characterize the differences in lake water temperature, so if it was due to, let's say, faulty placement of loggers, as a lot of literature has shown that there are urban effects on lake temperature, then the lack of relationship for the bluegill to respond to that warming may be due to stocking. So that movement of fish from around Missouri means that there's fish going from cooler areas to warmer areas to cooler, fish coming from out of state, and that stops really these populations from having an ability to adjust to these warmer temperatures. Additionally, again, this is assuming that there is some type of temperature difference. Because they're in lakes, the bluegill do have that ability to move to those lower, cooler depths and potentially keep away from any influence of the warming. With that said, that effect usually has a point where they can only get so deep, or only because the habitat usually isn't as ideal as when they have to move to lower depth in order to like maintain that good temperature thermal tolerance range. So that there will be kind of an endpoint to that where some type of change will occur, but maybe that hasn't happened yet. The final explanation is that we did correctly characterize the temperature differences in the lakes, so meaning that there isn't actually a temperature difference in the lakes that we studied. So that would, of course, explain why there's no difference in the bluegill thermal tolerance, because there's no difference in that water temperature that would that they would adjust to. So again, multiple possibilities there, but still very interesting. So overall, what are the takeaways here? These are two species of fish with highly overlapping distributions. So that means that they are very similar in where they are found and their ranges, and they're responding very differently to this heating. And a component of that is that human management of these freshwater systems may be disrupting the ability for fish to respond. And so adjustments may have to be made in order to allow some of these species to properly adjust to these changes in temperature. So here are my final takeaways from this study, and what I want you guys to leave here remembering. And that is, one, that urban heat islands allow for testing a species response to rapid changes in temperature and urbanization. And mainly, studying systems in urban areas can still provide really cool results and research into the effects of species that are found there. So a lot of times urban areas are kind of shied away from because they can seem really complex, but they can still offer like really, really cool systems to test how organisms will react to future changes. And additionally, this study is actually, I think, one of the first to document a freshwater fish responding to increases in temperature over a rapid timescale. So with the compostoma, it's one of the first instances of showing that a freshwater fish can increase its thermal tolerance in a short timescale. This work was published in Science of the Soil Environment earlier this year. It's Pagliaro and Knopf 2020. So if anyone would like to read a bit more about, more in depth about this study and the results and etc., just send me an email and I will send you a copy. And real quick, before I get to the acknowledgements, I did want to briefly mention what I'm up to now. So as I had said, I'm doing my PhD research at UC-Berkeley in the Ruhi lab. And I am now completely switching gears and looking at wetland restoration ecology. So I am working on a project that is funded through the California Fish and Wildlife for, it's a 3-year project. And this is being done in collaboration with USGS, the United States Geological Survey, and ICF. I don't know what ICF stands for. I looked it up many times, but essentially they're a company that studies fish within the San Francisco Bay. So what we are looking at, characterizing food webs in breached marshes. So research in the San Francisco Bay is, well, restoration is ramping up in the San Francisco Bay as they are restoring old levied or blocked off marsh area and back into the native tidal marsh. So meaning they're opening up that seawall and allowing for bay water to move into this marsh as well. And what we're looking at is how these food webs are being affected and essentially restoring through time. So how effective are these restoration efforts and what does that mean for the species living there? So yeah, it's a really exciting research. So this picture on the left is the current tidal marsh team on one of our first excursions out in the field. And the picture on the right, I don't know if it's the same for you guys, it may be flipped, but that is the breaching of our newest restored marsh called Tule Red that was breached in October 2019. So yeah, very different, but still exciting stuff. And if anyone has questions on that too, I'm happy to answer. But yeah, we'll move on. So for the acknowledgements, really quickly, I would like to thank the Knopf Lab and my PI, Dr. Jason Knopf, for helping, funding, supporting, etc., and making all this project possible. They were a great team and just very important to my success during my master's. And I'd also like to thank the Missouri Department of Conservation, specifically Kevin Mino and Denise Otto, as they helped me collect all the bluegill for my study. And with that, I'll take any questions. Here's my email and Twitter handle too, for you guys get in contact with me.
Thank you very much, Megan. Okay, if anybody is up for it, if you can try to find the mute button, you can go ahead and unmute yourself, and maybe in about 3 seconds from now, we can do a quick round of applause if anyone actually unmutes themselves. I'm seeing a lot of muted people here. Okay, here we go. So 3, 2, 1. Thank you, Megan.
Thank you.
Thank you.
All right. And we've got one question so far in the chat. If anyone else has questions, you can feel free to put them in the chat, or if you can figure out how to do the hand raise, you can do that, or just after this first question. So from Dan Pettis, he's asking, does the size or age of the fish matter for the CT max testing?
Yes, the size actually matters a lot for CT max testing, and that also kind of encompasses age within that. But smaller organisms are more thermally tolerant than larger ones. I don't, there's kind of a full explanation to why, but it's a common kind of trend. So with the CT max testing, you have to have a very narrow range of sizes. So when I was collecting and testing the organisms, I made sure to keep within a defined size range, as well as when I was running my statistical analysis, I made sure to, I included size as a part of that. And more of an interesting component because we controlled for size. When we're running the statistical tests, we're looking at if there are differences in size, it has less to do with that it affected the results in any way, but more that it's a possible mechanism that the fish have for being more thermally tolerant, if that makes sense.
Okay.
But yes, juveniles are smaller too. So I tested mainly juveniles for the age component.
Okay, we have several people saying great presentation, thank you. And then Bob Virag has a question. Was oxygen saturation monitored? And to what extent would the observed differences in thermal tolerance may instead be attributed to differences in oxygen tolerance?
No, we didn't look at differences in oxygen, mainly because, so one, in these stream sites with the flowing water, the oxygen isn't really an issue. And with the lake sites, they were all large enough that essentially like oxygen levels were the same. But we were mainly, looking at how the actual like thermal water effects were possibly pushing thermal tolerance to the side. But at that levels we were looking at, there really isn't that large of a like oxygen difference, if that makes sense. But it's still probably definitely a mechanism when it comes to responding to like with systems, freshwater systems, and having issues with increased heating, like let's say with those urban lakes where they were pumping in city water. Those, like, to stop from fish kills happening in the summer may also include with oxygen levels.
All right, any other questions? Okay, I'll go ahead and I have one. So can you think of any reason why maybe we would expect there to be a difference in response if you would look at different species of fish or even looking at invertebrates? Do you have any thoughts about that?
Yeah, I think that, well, one premise of my study is that sensitivity to warming as well as an ability to adapt to that warming is likely very different from species to species. And so both the fish species I looked at are considered warm adapted species. So they are adapted for warmer temperatures as it is. And I think that it basically wouldn't be good to just assume all warm adapted species are going to do great. So let's then just like move on. And as we saw, there's still a difference species to species wise, and that can be also due to how a species is able to adapt to changes in temperature. So the same with invertebrates. I know that there's a wide range in ability to, and sensitivity to warming and shifts. So it would be important to, look at, I think, species individual, overall, as opposed to trying to pool too much in terms of how they respond to changes in temperature. If that answered your question.
I think so. Yeah. And then a question from Glenn Clayton, excuse me. Was there an ability to study the same species from both lake and stream?
Great question. I wish. So I actually started off with the lake species and got my bluegill with MDC. And then we realized I had enough time to do another round, and I was I did want to have at least another species to look at, but then on top of it, we were interested in running essentially a bluegill in streams versus bluegill in lakes and seeing if that changed, and we couldn't find any. So it would be, in an ideal world, I would have also liked to run like a test looking at that same species in the two different systems, especially with the bluegill, to see if in that stream system they would have higher thermal tolerances. But alas, there were not enough bluegill for me to get.
Okay, any other questions? All right, great presentation. Thank you and good luck with your PhD research from John. And thank you once again, Megan, for coming and being the inaugural speaker in our fall RiverWatch speaker series. It was wonderful to hear about your work. And
I think someone has a raised hand.
oh, is there? Oh, yeah, I see Cece has a raised hand.
Sorry, Tanner.
Let's see. And I can't unmute you. I don't know. Cece, if you have a question, if you want to go ahead and type it in. In the meantime, just want to let everyone know that we do have more of these talks coming up. The next one will be on October 6th, and I encourage you to sign up if you haven't already. Thank you very much for being here tonight.